is coming on the other path. Yeah.
Okay, thanks. Thanks for the introduction. I hope everyone can hear me. Yeah, and thanks for the ISDA committee for the opportunity to present our recent study on the strongly coupled data assimilation with the coupled ocean atmosphere model RVCM, which is compared with the weakly coupled data assimilation. As we all know, data assimilation combines the model predictions with observations to provide a better estimate of the state for the system. And data assimilation has already been widely applied in the investigation of the ocean's atmosphere, land surface, and so on. And the coupled ocean atmosphere model can simulate the ocean and the atmosphere in one framework. And data assimilation for such kind of a coupled model can be divided into two groups, the weakly coupled and the strongly coupled. Traditionally, data assimilation analyze the ocean and the atmosphere separately, and no cross covariances are presented between these two components. An alternative way is the strongly coupled data assimilation, which is able to transfer the information between the different components like the ocean and the atmosphere using the cross covariance matrix. And in this study, we want to investigate the impact of simulating the ocean observations into the ocean and the atmosphere compartments in a coupled ocean atmosphere model. The coupled model we use is the RV climate model. It consists of the ocean model of FISM, including a sea ice model, and an atmosphere model, ACAM6, including a land surface model. And these two models are coupled through the coupling software OSIS3MCT by exchanging the fluxes between these two compartments. And for the data assimilation, we use the parallel data assimilation framework PDAF. So PDAF is open source. It's an open source software for in-demo forecasting and in-demo based data assimilation. It provides fully implemented and fully parallelized assimilation methods, and it can be easily used with many numerical models like our RVCM model. And for our numerical experiments, we use a global model domain. The resolution for the atmosphere model ACAM6 is 3063 with 47 layers. And for the ocean model FISM, we use unstructured mesh grids with varying resolution between 30 kilometers and 160 kilometers. The observation we use for data assimilation is the satellite sea surface temperature. The assimilation method is ESTKF, and we set up the in-demo site to 46. So for in the weakly coupled data assimilation, we only update the ocean variables, including the sea surface height, temperature, salinity, and velocity in 3 directions. And in the strongly coupled data assimilation, both the ocean and the atmosphere variables were updated. So the updated atmospheric variables include the air temperature, surface pressure, vorticity, divergence, specific humidity, and horizontal wind velocity. So as well as the ocean variables like the weakly coupled data assimilation. And the localization radius in the horizontal direction is 300 kilometers. And for the atmosphere, we also do vertical direction localization, which is up to 600 hectopascal. And the simulation period is 1 year with daily update. And for this 1 year simulation run, it takes about 3.5 hours with fully parallelized configuration using about 12,000 cores. The SST observation we use is level 3 data from the EU Copernicus. So it's a daily data set with data gaps due to the clouds, and it covers most of the regions except the polar region. So the original observation are interpolated to our unstructured mesh grids. So this figure shows the SST observation on January the 1st of 2016. The observation error is set to 0.8 degree. We carried out two strongly coupled data assimilation runs, one with and one without vertical localization, and one weakly coupled data assimilation run and one free run are also performed for comparison. And results are first evaluated for the ocean component. So the RMSE of SST was calculated by comparing the model simulation with the SST observations used for the data simulation, and the RMSE for the subsurface temperature and salinity was calculated by comparing the simulated simulation, the model simulation, with the independent in-for profiles data. And based on these RMSE values, we calculate the relative RMSE based on this to express this improvement compared to the free run. So now we can see the relative RMSE for the free run is 1. And compared to the free run, both the weakly coupled and the strongly coupled data assimilation improves the prediction of the temperature. And the reduction of the RMSE of SST can be over 60%, and the strongly coupled run without vertical localization with this one, so gives slightly larger RMSE for SST than the weakly coupled data assimilation run and the verticalized strongly coupled data assimilation run, and the strongly coupled data assimilation with vertical localization simulation gives similar the same RMSE for the SCDA as with weakly coupled data assimilation run. And globally, the SST bias is largely reduced by the data assimilation, and the bias patterns for these two strongly coupled runs and the weakly coupled run are very similar. Since our strongly coupled data assimilation directly updates the atmospheric variables, so in the following slide, we will concentrate on the impact of data assimilation on the atmospheric component. So here we list a number of atmospheric variables we selected for evaluating the data assimilation performance, so including the near surface variables like the 2-meter temperature and 10-meter wind velocity, and the air temperature, wind velocity, and specific humidity in the free atmosphere. So on the left-hand side, we show the 2-meter temperature difference between the model simulation and the ERA interim data. So in general, compared to the free run, the weakly coupled data simulation warms up the system almost everywhere. And the strongly coupled data simulation even strengthens this, leading to this less cold bias over the continent, like the south of China, India, east coast of South America, and north of Africa. And this kind of warming of by strongly coupled data assimilation also makes this warm bias even stronger or even larger in some regions. For example, like in Australia. So here compared to the weakly coupled data assimilation. And the difference between the two strongly coupled data assimilation runs, so with and without vertical localization, is relatively small. And regarding the 10-meter wind velocity, compared to the free run, both the negative and the positive biases along the equator in the Pacific Ocean and the Atlantic Ocean are strongly reduced by the data assimilation. But the reduction, let's say the bias reduction by the strongly coupled data assimilation is weaker than the weakly coupled data assimilation. And the weakly coupled data assimilation also reduced the bias in the southern and northern Pacific, which is not the case for the strongly coupled data assimilation. And the positive bias is strengthened by the weakly coupled data assimilation in the Southern Ocean, in the Southern Indian Ocean, and this is even stronger in the strongly coupled data assimilation. And both the weakly and strongly coupled data assimilation introduce a positive bias in the Southern Ocean. for example, south of Africa. And the free run actually shows the negative bias. Yeah. So similar like the 2-meter temperature, the difference between the strongly coupled data assimilation with vertical localization and the weakly coupled data assimilation, so the difference is minor, let's say. And this slide shows the zonal mean RMSE of temperature at different pressure levels up to 300 hectopascal. So between 650 hectopascal and 1000 hectopascal, in the lower half of the troposphere, the zonal mean RMSE of temperature is reduced everywhere by data assimilation. And this is especially in the tropics and lower latitude between 30 degrees north and 30 degrees south. And between 900 hectopascal and 500 hectopascal, the RMSE is slightly increased by the weakly coupled data assimilation in the Arctic, but the two strongly coupled data assimilation runs reduce them. And data assimilation increase the RMSE close to the equator between 10 degrees south and 10 degrees north. Yeah. Between 650 hectopascal and 450 hectopascal for both the weakly and the strongly coupled data assimilation. And compared to the weakly coupled data assimilation, this strongly coupled data assimilation gives larger RMSE between 25 degrees north to 25 degrees south, but still smaller RMSE in the high latitude. And similarly, the difference between the two, the strongly coupled data assimilation with vertical localization and the weakly coupled data assimilation is again very minor, except for this positive influence in the Arctic. So the assimilation also influences the wind at different pressure levels in the atmosphere. Between the 800 hectopascal and 1100 hectopascal, zonal mean RMSE in the equatorial region is reduced by the weakly coupled data assimilation and the strongly coupled data assimilation with vertical localization. And the strongly coupled data assimilation actually gives very similar RMSE at the free run. And so the strongly coupled data assimilation gives actually larger RMSE between these regions, so 25 north to 25 south in the free run, and also the weakly coupled data assimilation, so up to 300 hectopascal. But for the rest of the regions, the RMSE is reduced. So these two, actually, the strongly coupled data assimilation with vertical localization and the weakly coupled data assimilation, so they performs always quite similar. Also here for the wind velocity. So a further effect of the assimilation is visible in the specific humidity. And the RMSE along the equator, especially in the higher atmosphere above 600 hectopascal, is largely reduced by data assimilation. And slightly smaller RMSE is found in the southern hemisphere north of 40 degrees south. So for the weakly coupled data assimilation compared to the free run. And the RMSE in this region actually is slightly larger in the strongly coupled data for the strongly coupled data assimilation than for the free run. And like for the temperature, so the weakly coupled data assimilation somehow worsened the state in the Arctic region. Yeah, but the strongly coupled data assimilation actually improve the simulation in this region. And similar like the temperature and wind velocity. the humidity difference between the strongly coupled data assimilation with vertical localization and the weakly coupled data assimilation is mostly minor, except for this Arctic region, where here we see the smaller RMSE for the strongly coupled data assimilation with vertical localization. And then comes to the summary of our study. So the strongly coupled data assimilation of SST observation actually yet similar performance in simulating the ocean as for the weakly coupled data assimilation. And for the atmosphere, the strongly coupled data assimilation generally or overall slightly worse the results than the weakly coupled data assimilation if no vertical localization is carried out. And if we do vertical localization in the atmosphere, so the data assimilation increments can be constrained directly to the lower troposphere. So the difference between the strongly coupled data assimilation and the weakly coupled data assimilation is quite minor. So except in the high latitude region, especially in the Arctic region. So in the Arctic region, actually, if we do or do not do vertical localization, the strongly coupled data assimilation always improves the atmospheric state, including the temperature, humidity, and the wind velocity. And that's all from my side for this presentation, and thanks for your listening.
All righty, thanks a lot for your presentation. That was quite interesting. The first question we have from the Etherpad is by Sergei Frolov. He's asking you, is your strong result in the Arctic connected to your possibly stronger skill in ice analysis?
Actually, we don't focus on the ice. Actually, we don't do any special treatment for the ice, if I understand correctly your question. So we only update the ocean state and the atmospheric state, and we use only the SST. So we don't do anything with the ice.
Okay, and I have another question. Sergei was before Sergei was showing regions in the planet where there were processes that were very coupled between atmosphere and ocean. So in the mid latitude, he was showing the Gulf Stream, for example, and then he was just showing tropics. Did you find those regions to be greatly benefited by strongly coupled data assimilation?
Okay, here I didn't have a figure for that, but actually, we found this not in the mid latitude, but actually we found in some regions this bias, for example, in the atmosphere, like the 2-meter temperature and wind velocity. So here shows the bias of the 2-meter temperature, for example, for the free run and the weakly coupled data assimilation. So we found in some regions these bias are quite large compared to the other regions, like the Gulf Stream. Actually, we also found them in this SST bias. So, sorry, my computer doesn't work quite well.
All right.
Yeah. For example, in some regions, we already found this large bias for the SST, even if we directly assimilate SST, and we can't actually remove this large bias either by weakly coupled or strongly coupled, and this actually is still the case for the like the 2-meter temperature, the atmospheric variables. So, but if we compare the difference between the strongly coupled and weakly coupled, so it's not very clear actually. Yeah. For example, here if we remember, this large bias exists there in the SST, but if we have a look at this difference, actually we didn't see the large difference, especially in this region. So let's say the difference between strongly and weakly coupled assimilation doesn't give such kind of
I see.
bias in the latitude.
I thought Philip Brand was starting to write a question and then he erased it. Thank you, Philip. Well, Lars has entered the comment to Sergei's question in the Etherpad, and if anyone else wants to ask more questions to Guy, feel free to just write them down, and I'm pretty sure he will be able to respond in text.
Yeah.